Hello and welcome. Have you ever wondered why a straw in a glass of water looks like it's broken? Well, in this explainer, we're going to break down the incredible science behind that illusion. We're talking about the bending of light. It all starts with something you've probably seen 100 times. A bit of everyday magic, really. You put a pencil or a straw in a glass of water, and it looks bent right where it hits the water. So what on earth is going on there? Well, that strange effect actually has a name. And it's the hero of our story today, refraction. Basically, it's just the scientific way of saying that light changes direction when it moves from one transparent material to another, say, from the air into water. Okay, so to really get to the bottom of this, here's what we're going to cover. We'll start with that bent pencil mystery. Then, we'll figure out why light changes its speed. After that, we'll get into the rules of how it bends, explain the famous Snell's law, and finally, look at where you can see refraction all around you. Ready? Let's dive in. All right, first things first. Let's solve this mystery once and for all. That bending you see, it isn't just an illusion in your brain. It's a real physical thing that's happening to the light itself. So, here's the number one reason, the big secret. The speed of light isn't always the same. Sure, it travels at its absolute fastest in a vacuum, but the moment it enters something like water or glass, it slows down. And it's that sudden change in speed that forces the light ray to pivot, to actually change its direction. And now this change in speed is tied directly to a property we call optical density. And just to be clear, this has nothing to do with how heavy or physically dense something is. It's all about how much a material gets in the way of light and slows it down. Think of it this way. An optically rarer medium, like air, is like a wide-open highway for light. It can just zoom through. But an optically denser medium, like water or glass, is like hitting rush hour traffic. The light just has to slow down. And we measure this traffic using something called the refractive index. The higher that number, the slower the light goes. So if light bends, does it just bend randomly? Any which way? No, not at all. It actually follows some very specific, very predictable rules. And a classic experiment with a rectangular glass slab shows us exactly what those rules are. Okay, take a look at this diagram. You can see a ray of light coming from the air, entering the glass slab, traveling through it, and then popping back out into the air on the other side. Just look at how its path changes direction, both when it goes in and when it comes out. And this whole process reveals two simple, absolutely crucial rules. First, when light goes from a rarer medium to a denser one, it bends towards the normal. And the normal is just an imaginary line we draw at a 90-degree angle to the surface. Rule number two, when light goes from a denser medium back to a rarer one, it bends away from that normal line. Towards when entering, away when leaving. Simple as that. So, what's the final result? Well, because that bend going in is perfectly canceled out by the bend coming out, the ray of light that emerges is perfectly parallel to the path it started on. It hasn't been thrown off course permanently, just kind of shifted sideways a little bit.
Now, these rules and observations aren't just some casual guidelines. They're captured precisely in what we call the laws of refraction. And this is where we get into the math that lets us predict exactly how much the light is going to bend.
So there are two main laws. The first one's pretty straightforward. The incoming light ray, the bent or refracted ray, and that normal line we talked about, they all lie on the same flat surface. But the second law, that's the really powerful one. It's known as Snell's law, and it gives us the exact formula connecting the angle of the incoming light to the angle of the bent light. And here it is, the famous equation for Snell's law. It says that the sine of the angle of incidence, that's I, divided by the sine of the angle of refraction, that's R, is always equal to a constant number for any two specific materials. This little formula is the key to calculating exactly how light will behave. So what is that constant we're talking about? Well, it's the refractive index we mentioned earlier. It's a special number for each material that literally tells you its light-bending power. And we calculate it by dividing the speed of light in a vacuum by the speed of light in that specific material. Okay, so why does all this matter? Why is this so important? Because this fundamental principle, refraction, is the secret technology behind some of our most incredible inventions, especially the lens.
Yep, every single lens, whether it's in a camera, a telescope, a microscope, or even your own eyeglasses, is just a piece of glass or plastic that's been perfectly shaped to control refraction. A convex lens, which is thicker in the middle, bends light rays inward.
gathering them to a single point. A concave lens, which is thinner in the middle, does the exact opposite. It spreads the light rays out. This simple, controlled bending is the magic that lets us see tiny cells or gaze at distant galaxies.
So, as you can see, refraction isn't just some idea in a textbook. It's why a swimming pool always looks shallower than it really is. It's why stars appear to twinkle in the night sky. It's how a prism can split white light into a beautiful rainbow. Now that you know the secret, the real question is, where else will you spot it changing the way you see the world?